I joined CAD Centre as was in 1972 as a programmer. I had some interviews with ICL, who staffed the centre on contract to what was then the Department of Trade and Industry. Had some interviews, got a job offer at this place in Cambridge, had very little idea what it was all about, and turned up here in 1972 and started working for Dick Newell as a programmer. And I was there for 4 years, from 72 to 76.
I joined CAD Centre in 1970, having been with ICL for 2 years before that. And I actually did one of the first ever A-levels in computer science in 1968, and then joined ICL. After 2 years as a trainee, it was time to move on, and I was very fortunate to get a position at the CAD Centre in Cambridge, and I was there for almost exactly 10 years, leaving in 1980.
Mm-hmm. I did a natural science degree in Cambridge, in chemistry in fact, then did a PhD in physical chemistry, and during that I got more interested in playing around with the computers rather than actually doing the job, although I did complete the work. I finished my PhD in 1970 and saw an advert in the Cambridge Evening News and thought, oh, that looks interesting, it's local, I'll have a go. So I applied and I got appointed in October 1970, a bit after Chris, who arrived a couple of months before me, and I got involved initially in the sort of the graphics output stage in a package called Gina.
The CAD Centre began in, well, the first seeds of it must have been in 66 or 67, when Tony Benn, who was then the Minister of Technology, in the so-called white-hot technology era, decreed that there should be a computing centre for engineering run by or financed by the government. And so they looked around for where this should be, and at that time Ferranti had built a computer specifically for Cambridge University, which was called the Titan. And Ferranti decided that this computer was obviously something that was worthwhile making as a commercial computer. And they built another one, and it didn't sell. And so the Ministry of Technology kindly picked it up and said, right, well, this is obviously the central computing engine for this new engineering computing centre. So where shall we put it? Well, it seemed logical to put it alongside its twin, which was at the University Computing Laboratory in Cambridge. And before it became the CAD Centre, it was called the MinTech Atlas Centre. And for 2 years, it was there being commissioned, and there were a group of people, some of whom I'm still in touch with, who came in as school leavers and were all doing tasks associated with commissioning this large computer. And then finally in 1970 it started selling computer time on a timeshare basis, so that people dialed in to use this large computer to engineering companies around the country. And there were everything from who are the people in Gloucestershire, Cheltenham,
GCHQ.
GCHQ was a customer. We had the Admiralty Underwater Weapons Department, I remember, who were a customer, and their username was Torpedo. After a couple of years, somebody in the Admiralty discovered this and said, no, you can't possibly have that name. This is far too risky from a security point of view. And so their username was changed to AUWRE, which of course nobody would ever guess was the Admiralty Underwater Weapons Research Establishment.
Before the CAD Centre opened for business in 1970, what had happened was that the university had installed their operating system in the Atlas II, Atlas II incidentally, and at about 1968, 69 or sometime, they wanted to move the Titan. So they had to turn it off and move it to another part of the laboratory. And what happened then was the entire university computing network was switched to the Atlas II at the CAD Centre. So when I was doing a PhD, I was actually at one stage using the Atlas II rather than the Titan, which was currently in bits being moved from one room to another. So to some extent, the initial troubleshooting of the Atlas II was sort of sorted out by the University Computing Service, turning it into its workhorse. And this was before it actually opened for business with real live commercial customers in 1970-ish.
Another thing that's worth mentioning is really Arthur Llewellyn and his role in the whole thing. He was Arthur had been involved in radar research during the war and was a key scientific advisor to Tony Benn. He previously worked at NATO as a scientific advisor, and he was really in many ways responsible for coming up with this idea, which he then ceded to Tony Benn. And Tony's agreed with it, and apparently they were all on a flight to Germany one day, and he said, well, where are we going to put it? And Arthur said, I've got an idea, I've got a site picked out. Fine, go ahead and do it. And what about a computer? And he said, well, I just happen to know there's this spare atlas sitting at Ferranti. Good, we'll do that as well. So, and then, of course, Arthur was appointed to be the first director. So he really had an absolutely key role in making the whole thing happen, as well as managing it when it came into existence.
In the initial recruitment, there were two parallel teams. There was a team of practical engineers and a team of computer programmers. So there was a civil engineering group, there was a chemical engineering group, there was a mechanical engineering group, and at the head of each of these groups was a so-called consultant, and the consultants, all of whom were data skill employees with one exception. Each group leader came up with problems that were known in their particular area. So I remember one of the early ones was a mechanical engineer called Tony Edwards, who had a particular interest in marine engineering, and one of the big early projects was on analysing torsional vibration in propeller shafts on ships. Well, you know, it's a fairly esoteric area, but Tony knew this was a problem. He had a junior consultant called Ken Davis who was interested in this problem, and they got together all the research, and some of the teams of programmers were set to in putting this into code. Then there was a chemical engineering group which was headed up actually by another civil servant. I was wrong, there were two. Michael Leasley, and his sidekick was Peter Winter. And they, together with Dick Newell, who has been mentioned earlier, who was one of the people more on the programming side, though Dick was a civil engineer by training, wasn't he? And he'd done a PhD on pipe routing. And so Mike Leasley and his crew sponsored the project for actually turning Dick's PhD into software in a lot of ways, wasn't it? And that became a system called PDMS, which Aviva are still selling today. And it was for routing pipework around chemical plants, petrochemical.
Well, what it looked like was a little terminal, and was behind it, looking at the size of this room, was a computer which just about filled this room, I would have thought. It would have probably fitted in this room.
It was a number of discrete cabinets.
It was.
You would have seen a lot of things that look perhaps like that safe over there, which double doors on the front, and difference being that if you open them up, there are just circuit boards stacked up in there. There were 6 tape decks. There was a typewriter that Michael mentioned, which was an IBM golf ball.
Yeah.
And
There was 3 cooling towers on the roof to get rid of the heat.
Yes, it was water
Steam-
cooled.
Steam was pouring out of those, or rather water vapour was pouring out of those constantly. And as every computer had in those days, a false floor about 2 feet deep for all the cabling to be routed through.
And it had a disk, which was probably took, I think the disk was about 200k, wasn't it, altogether?
128.
It was a disk drive,
Yeah.
and it was in a cabinet which was about 8 foot tall by about 4 foot wide by 6 foot long, which had about 20-pound magnesium alloy discs in it,
That's right.
held together by 6 bolts. And when there was a head failure, as there was often, and the head was about the size of your thumb, whereas today you can hardly see it in the microscope. The engineers came in, took the lid off, pulled all the bolts up, pulled the discs up one by one, found the faulty one, replaced it, put all the discs back in, bolted it up, and then wrote the data back to where it had been.
Meanwhile, we all went to the pub.
We did at one stage try to double the size of the disk on the Atlas II, and there weren't many disks that were suitable, but one was at Aldermaston, because they also, I think, used an Atlas.
They did. They had another
Yes.
Atlas too.
Yes, Aldermaston Atomic
An
Weapons.
Atlas one.
They had
And-
Atlas 1.
Yes.
And we tried to persuade them, or John tried to persuade them, to let us have the disk. And the only way they would let us have the disk was if they could destroy it first, because of the secrets on it. They didn't believe the fact that we could actually erase the data. The only way that the people at that stage thought they could do it was to actually smash the disk, which wasn't really very helpful for those of us who wanted to have a new disk. The other thing, of course, is that the Atlas had to have, I think it was 4 full-time people looking after it all the time, because it would, every so often, a transistor somewhere would go, because it was all in discrete transistors, so no such things as integrated circuits. And every so often bugs would appear in the operating system, so they had to be re-sorted. And I think there were 4 full-time people, weren't there?
But that was just on the software side.
But then there was a whole batch of engineers as well.
There
There
were hardware engineers, 6 or 8 of those.
So whenever the machine stopped, they'd all pile into the machine room and look at all these lights on this huge display and try and figure out what had gone wrong from the light. It's worth emphasising this is one of the very few online time-sharing systems with terminals working anywhere in the world at that time. And there were all around the CAD Centre, there were old ASR33 teletypes connected, a few very early VDUs, and then I think even more revolutionary, very early days of connections out to terminals on customer sites. So customers were programming on their own sites with 110 bits per second acoustic couplers. So in contrast, when most of the world was working by, you turned up with a whole pile of punch cards, you handed them over, you got a result back. People were actually typing their programs, debugging them, running them, getting the results back instantly, and programming in a very, very efficient way for the time. And it's also worth mentioning that the Atlas II was, at that time, it was the supercomputer of its era. There was one other machine, an IBM machine, which, depending on what test you ran, was either a little bit faster or a little bit slower, and they were just generally judged to be about the same. So we had one of the most powerful computers in the world at our fingertips, and that felt good.
Absolutely.
By today's standards, of course, nobody was doing very heavy computing. No, it was complicated, and if you were doing calculation on vibration in propeller shafts, then you knew it was going to take a long time to run to completion. If you were doing surface modelling, which was another thing we got into in early days.
Because of the way the Atlas worked, certainly when I was using it as a student, you could not run interactive programs. You had to create your program and just send it down the wire and wait for the result to come back. But when we got to the CAD Centre, at least those working at the CAD Centre, could then start writing programs which were genuinely interactive and say, ask you a question and give the answer, ask you a question and give the answer, and then compute. And that was a significant advance, I think, that a multi-access system could actually allow you to do that. Because certainly for the students, you are only allowed to stick your program into a file, stick your data into another file, send them both down the wire, and wait for something to come back, because your program will then be paged in and paged out as required. But once we got to and I think there were some changes made in the CAD Centre operating system that allowed the ability to write interactive programs, which I think became very, very important for the future development of CAD, because you could then start genuinely testing ideas out with different values and seeing the results come back to you. whereas prior it was a sort of remote access batch system.
I think the other thing that was very important in those early days was all the graphics work that went on, because you're into a completely different dimension. Instead of having some numbers coming up on a sheet of paper in front of you, you have a graphic system that you can interact with. Now, originally the graphics interaction itself on old Tektronix, particularly old 4010 and 4014 green storage tubes, was somewhat crude. In you had two little, nothing as sophisticated as a mouse, where basically you have two wheels inside it, but you had to twiddle these wheels and watch a crosshair on the screen and nudge it until you got it in the right place, then press a button on the keyboard. And, it was interaction, but of a pretty crude form. But very soon in the development of PDMS, we began to get very sophisticated graphics. Another thing that was going on at the same time was there was a lot of graphics going on what were known as satellite computers, where there was a link to Atlas, and typically you do your programming on Atlas, and either there would be a link where you could download it onto the satellite computer, or more often paper tape. So you picked up a roll of paper tape, fed it in, ran it, and so on. So there was an Elliott 905, PP9, and a few other devices from time to time.
Yes, I mean the Elliott 905 could actually work over a phone line, because there was another Elliott 905 in the University Engineering Laboratory. But the PP9 had a parallel interface, so it could only work in intimate, close contact with the Atlas. You have to remember that in those days, the telephone network could either communicate 110, 110, or 9.6, 75. So you could send 75 bits per second down the wire and get quite quick pictures back at 9.6. But those are the maximum speeds that telephone lines could possibly work at. Nowadays you've got, whatever you've got, I don't know what the numbers are, megabits per second. But in those days, partly because of the GPO monopoly, they simply didn't increase the speed. You had to buy a private wire, and I suppose this is part of it, in order to get any sort of faster communication.
There was even a project slightly underway to do a portable operating system
There was
before
indeed.
anybody had heard of Unix.
Yes.
And it was actually happening at about the same time as Unix development was going on in the States.
It was.
Portos it was called.
Yes, that's right, yeah. And I think this use of portable Fortran actually became very important because, of course, when the Atlas eventually closed down, we had a huge legacy of old code which we had to move on to something else. And I think that's when we moved over, largely from the Atlas largely to prime computers, which was the sort of next stage of the computing power that we used, that became very important because we were not writing in the Atlas dialect of Fortran, and the ability to move programs around became much more important. And of course these days, you do have standard versions. Although you've got 3 separate browsers, for example, on the internet, they're all pretty well accept the same version of JavaScript, which is a sort of equivalent idea, or HTML or whatever. So the same sort of ideas have sort of fed through, and it's crucially important to be able to handle ancient legacy programs. Another slightly out of order remark is that I remember when we were looking at the replacement for Atlas, which was becoming on its last legs at that stage and harder to keep going. The virtual memory was crucially important. I remember I was mentioning it before, but the PDP-11, which is again a very important program used for engineering type projects. The only way you could use that when you had big programs was to do overlays which you controlled yourself.
And when we were doing PDMS and trying to do port it to other machines, when we found a virtual memory machine, a machine that wasn't a virtual memory machine, we just all thought, oh God, this is going to be hard, and it was terribly hard.
The Atlas could handle quite big programs, but they often would not fit onto a PDP-11. So you had to sort of work out chunks of code which you could then read in from disk, execute that chunk of code by a sort of central core, and then maybe bring in the graphics output as a separate process. You couldn't have the two residing in memory at the same time because of the nature of the operating system and the nature of the address space in the PDP-11. The Prime allowed you to write very, very big programs because it had a virtual memory type approach. Essentially, you have a big address space. You don't need actual physical memory, which is the size of that. You behind your back, the operating system is sort of handling the swapping in and out of code from disk into the physical memory, which is the sort of solid state stuff, from what then was the disk, which was the magnetic stuff. Of course, now there's huge differences, and disks are no longer magnetic. They're solid state themselves. But in those days, you had the sort of slow disk and the fast physical chips. Well, primes sort of came in
74, 75.
Yeah. We stuck with those really for quite a long time, because really the next thing was the
VAX.
Well, the VAX, of course, yes, which was a
It sort of came a few years after the Prime and was very, very similar.
very similar. It's a bit like the PBDP-11 with a virtual memory operating system. That's right. So that also came along, and we started writing programs that would run on both, which I think was what I've already talked about with Portable Fortran. But obviously the up and coming thing was the desktop PC. But they were, at least initially, they really suffered from all the problems of very small address spaces. So you couldn't write big programs on them. And so we really didn't. There was another sort of in-between phase. I'm just trying for the life of me to remember.
The kiosk.
Well, it wasn't only that, actually. There was also, what were they? The Sun Microsystems.
Oh, yes.
Sun Microsystems. They ran Unix, and they became very important for running this sort of program on CAD type programs. Now, I don't know to what extent the CAD Centre was involved there. I got involved with them rather after the CAD Centre.
Yeah,
I did too.
Again, yes.
I think that. I remember a quote from John Chilver. No, it was Peter Gooding, who was the guy in charge of the operating system on the Atlas, and he left with the demise of the Atlas. He wasn't going to work on anything else. And he said, the trouble with the world is that we're getting more and more powerful computers in order that people can write less and less powerful, less and less efficient programs.
Mm-hmm.
And so you were getting all this extra computer power, but you weren't actually gaining very much in terms of ability to run software. And the other thing that was happening was that there had been, and this was John Chilvers saying, there had been a sort of a sequence of events in the history of computing where you had started with very big valve computers that took up the whole room, and people queued up outside the door to use them one at a time. And then somebody came up with the idea of an operating system. And so these big valve computers could then be shared between lots and lots of people. And this was great, but they got slower and slower and slower because they tried to squeeze more and more people in. And so then somebody says, I know what we'll do. We'll have what we'll call the mini computer. And we'll allow that because it'll be so cheap that people will be able to afford to have one for each user. And so along comes the Prime, the PDP-11, and such like.
VAX.
Well, the VAX was later because that was multi-user. Because that was the next. That was the but it was the next phase was to actually take these mini computers and say, there's so much power in here, we could have several people using it at once. So they got slower and slower and slower again, and then they came up with a PC. And actually, I did once see an advertisement for ICL that had the bright idea of a PC that could be used by several people. But fortunately, that never caught on, I think. Yeah. But it was interesting that you went through this cycle of single user, multi-user, single user, multi-user.
Well, with the Suns and so on, you got, and then later the VAX stations, you got into the idea of a powerful engineering workstation. But then, of course, you needed to network those for storage and so on. And so the ideas of very networked computers started to come to the fore. And certainly, once we all left CAD Centre, we're doing later things. The software where we were selling there was typically on an engineering workstation with some kind of disk server and a network.
Usually running Unix.
Usually running Unix.
In those days, it wasn't until much later that you could actually run it on a PC, because the PC operating systems didn't allow that sort of thing. Because nowadays you can run Unix on anything. It was Linux and all of that sort of thing. But then it was very much you had to have a big machine to do it. And these were powerful desktop, but they cost several £1,000s each, didn't they?
Oh, yeah.
Compared with what you can buy for £300 or £400 today, or in my phone, the amount of computing power is negligible. But in those days, they were very, very important as local workhorses for running this stuff on.
A lot of these you can trace, not directly in some cases, but the Prime system, which came out of a system, it was a Honeywell system, which could trace the origin of the operating system back to the Multics system. The Prime system could be traced back to Multics as well. There was an awful lot of the ideas.
And Unix, of course. It's the IX at the end of where
yes.
So
That system, which was MIT, I think, was Multics.
I think it was.
That was very influential in a lot of ideas about the way the virtual memory system ran and security and all sorts of other things. I think there was a parallel idea at the site as well, Chris, that a lot of the original ideas, the additional objectives had been achieved, and that CAD was now beginning to become mainstream, and that it didn't need just one centre for it to blossom in, and the phase of taking the message out there to industry and saying, use this stuff. The industry had largely started to embrace those ideas, and it had a momentum all of its own.
Absolutely, yeah. I mean, what happened was that there were four of us, basically: John Chilvers, Dick Newell, Tom Sancher, and myself. I think probably mostly by Tom, actually, who decided that working in the confines of the CAD Centre, we got sort of stuck. We'd also got some ideas for other ways of applying CAD. I mean, I got very heavily involved with a Swedish company called ASEA, and we'd written them a special purpose computerized drafting system, which I did most of the implementation of. And we'd begun to realise that interactive computer design and things like circuits, electronic circuits initially, was becoming something which had quite an interesting market, and we wanted to basically exploit it for ourselves. So four of us, John, Tom, Dick and myself, I joined about a year after the other three, formed this company called Cambridge Interactive Systems. And we started off by doing some freelance work on television adverts, lots and lots of money, no support, because you produce a film and then you've forgotten about it and you can move on to the next job. But we used to charge them the earth for these 10-second bits. But in the background, we were using the money that was coming in from that sort of thing for developing a new computerized drafting system initially, 2D initially. But then we got some ideas of how we could extend that to handle 3D models. It's all very well producing lovely shaded pictures of things, but in those days generating the models from which you wanted to draw a shaded picture was really quite difficult to actually, to mathematically describe the structure which you could then feed into a shaded picture viewer. And so we had some ideas of how to do that, and that's really where we started then working, and we eventually ended up with a product called Medusa, which was it produced 3D output, but it did it via 2D drawings, which was really quite an original idea at the time. And we started selling that, and we gradually started giving jobs to former computer-aided CAD Centre people, including Chris and various other people. That's why Chris has said, and including Alan as well, yes.
I think it's tremendous. I think it's had a huge impact on Cambridge. When you look at the number of people who have worked for successor companies and companies that have spun off, there are
I think you're absolutely
dozens,
right.
if not hundreds, of businesses where you can trace it right back to CAD Centre.
I mean, when the Cambridge Phenomenon was first written, that book by Siegel Quince,
Siegel Quince 60, yeah.
it was, the CAD Centre was, the university was in the middle of the circle, and then outside that there was Pi and the CAD Centre, and it was right there.